everyone. Welcome to this, the 21st session of Astro Adda, popular astronomy talks with possibilities of quantitative work, simple work which could be taken up by participants. And welcome to this session organized by Nehru Planetarium, Nehru Memorial Museum and Library, and the Public Outreach and Education Committee, Astronomical Society of India. And to take us through this detective story where we no longer are going to invoke Sherlock Holmes, but we are going to look at the reality of black holes. Professor Prajwal Shastri is with us. Very happy that you are here with us, Prajwal. And Professor Prajwal Shastri, her interests have been in active galaxy, supermassive black holes. So she is going to take us through this walkthrough of black holes and the most recent excitements which resulted in the Nobel Prize, along with other aspects of black hole studies. Professor Shastri has worked at a number of locations: Tata Institute of Fundamental Research, Indian Institute of Astrophysics, several other locations. She is member of many international and national committees, and she is very keen on outreach. So I hope that we will have many more collaborations and other projects together. Prajwal, I'll hand over to you.
Thank you very much. Can you hear me?
Yes.
Okay.
And
yeah, thanks very much. Namaste, everybody. It's a pleasure to give this talk to these kinds of audiences. It's always a pleasure to work with my longtime good friend Ratnashri. Yeah, it's unfortunate that I can't give this talk from the Delhi Planetarium. I always enjoyed that.
we'll have that.
Nevertheless, to make use, make the best of it. Okay, so if you ask the question, what would black holes look like, or what are black holes? I mean, naively, this is what they would look like just black. So black holes are chunks of space-time from which even light does not escape. So why do we say space-time? That's just a fancy way of saying that for any complete description, I need to specify both space and time. So for example, if I say I'm here at the southwest edge of Bengaluru, then I have to say when, because I wasn't here maybe last week. So I have to say I'm at the southwest edge of Bengaluru now. So that's one intuitive way of understanding what space-time is. But you can also trivially think of it as just space. So black holes are chunks of space, or space-time more precisely, from which even light cannot escape. So how do we get an intuitive feel for this? So I use the word escape, and we all know that if we think about the Earth, for example, and we think about throwing something from the Earth, it will normally fall back to the Earth. If we throw it a bit faster, then it will go a bit further, but still come back to the Earth. However, there will be a speed, which we call the escape velocity, with which if we launch something, it will escape the gravity of the Earth and go out into outer space. So that is something we call the escape velocity. We know that for the Earth, at the surface of the Earth, it is about 11 kilometers a second, or 40,000 kilometers an hour. Similarly, the Moon has an escape velocity of about 2 kilometers a second. So we might remember, most of us have learned this formula in high school. We might remember that this velocity, the velocity with which you need to escape, is basically related to the mass of the thing you're trying to escape from, and how far the surface of that mass is from its center. So that is what is encapsulated in this formula. So m is the mass, v is the escape speed, G is something we call the gravitational constant, if you remember that. And the symbol R represents the distance between the center of the thing you're trying to escape from and the point where you're trying to escape from. So similarly for the moon. So now, suppose we squeeze the Earth. That is, we keep the same mass of the Earth, but we squeeze it to a smaller size. Then what will happen is this factor R will. I just had a question for Ratna. Ratna, can you see my cursor? Ratna, can you see
Uh,
my cursor?
yeah, actually, my site. Yeah. Yes, 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 yes,
Okay. Okay.
yes.
Right. So if we keep the same mass of the Earth and squeeze it to a smaller size, then this m remains the same, but this r will decrease, right? And therefore the escape velocity will increase. Uh, now, suppose we imagine that we squeeze it so hard that the escape velocity becomes the velocity of light. Now, we know that the velocity of light is 300,000 kilometers a second. And so in this formula, if we substitute that, what we get is a relationship between the size of the object, which is represented by r here, and the mass of the object. The other things are constants. Right? So in other words, if you have a given mass, this formula will tell you a size to which, if you squeeze it, light cannot escape from. So it turns out that for the Earth, you have to squeeze all of its mass into a marble size. And if you do that, then light cannot escape from the Earth. So this is an idea that people thought about a long time ago. So two examples of people who have documented this idea are John Mitchell, who was a clergyman, a scholar in England, and Pierre-Simon Laplace, who was a polymath in France. And they considered these ideas, and they did talk about objects being so heavy that even light cannot escape. Now, Einstein proposed the famous theory of general relativity in 1915, and it was a theory which had a very different way of looking at gravity. So no longer thought of it as a force, but as a property of space-time, which is like the fabric in which everything sits. And so the idea was that if there is a mass in that fabric would curve, which is sort of what is represented in this figure. So one qualitative description of the general theory of relativity, which was a very beautiful description given by a relativist called John Wheeler, is that mass tells space-time how to curve, and space-time tells mass how to move. So in other words, if you think of the fabric of space-time curving like this, you can imagine that if anything approached this mass, then it would sort of be driven by this curvature and it would eventually fall into this mass, which is what we experimentally see. So this was a very different way of thinking about gravity. And every mass causes this sort of curvature. So your mass, my laptop mass, every mass you think of. But we don't sort of notice it in everyday life because it is a very small amount. So we don't really see the curvature of space on a daily basis. Anyway, so Einstein proposed this theory, and in the same year, somebody called Carl Schwarzschild predicted a consequence of this theory, and he came up with the same identical formula that John Mitchell and Laplace had come with earlier. So, does that mean that Einstein's theory predicted black holes? So that was not how they thought of it at that time. So even though Einstein's theory of relativity predicted several things which were experimentally demonstrated. So for example, because the theory says that mass tells space-time how to curve, you can imagine that light will, in this picture, no longer travel in straight lines if it is traveling near a mass, because light takes the shortest path between 2 points. And the shortest path itself is curved when there is a mass present somewhere. So the light will follow that curve. And basically, the general theory of relativity predicted that light would bend in the proximity of masses. This was, of course, not expected to be measurable in everyday life, but when the total eclipse happened in 1919, Arthur Eddington did this famous experiment and demonstrated with the help of stars which were near the eclipsed sun that indeed light bent exactly the way general relativity predicted. And now it is part of our daily experience because GPS satellites have to take into account this bending of light in order to work properly. So, but even though there was this demonstration by Eddington, there was also the a demonstration that the perihelion of Mercury was precessing exactly the way general relativity predicted. There was still a lot of doubts about this solution or consequence that Karl Schwarzschild had found for the general theory of relativity. Even Einstein himself didn't quite accept that this was a black hole, because basically this consequence was saying that there was this point where the curvature of space-time was infinite, and that was something that was very disquieting for people. Now, going back to John Mitchell and Laplace, they knew that these kinds of objects that they predicted had to be cosmic, because they imagined that if you squeezed the Earth's mass, you had to squeeze it to the size of a marble, which is like impossible densities. So they knew that in order to have realistic objects of this sort, they had to be very, very large, very, very massive objects like stars, not everyday objects that would see around, not even the Earth. So they knew that these black holes that they were thinking about had to be cosmic. But then they were black holes, so obviously they were very hard to find and nobody had found them. Also, there has been no evidence for black holes in the laboratory. So there has been speculation about micro black holes or black holes the size of an electron or something, but none have been found so far. So, okay, so before going further, there's just a small digression I want to make. So in astrophysics, we tend to use somewhat different units because in the things we're trying to study, things are so big, the spaces are so vast, and the powers are enormous. So for the unit of mass, we actually use the mass of the sun. So the sun is about 2 into 10 to the power 30 kilograms. That's an enormous amount of mass. So we use that as a unit, and we say something is half a solar mass or 3 solar masses. The unit of power or luminosity, we also use the luminosity of the sun, and we that's denoted by this term here, like L with a subscript symbol which represents the sun, and we say 1 solar luminosity or half a solar luminosity. Okay, so to go back to the story, in 1931, we all know that Subramaniam Chandrasekhar worked on the physics of stars, and he showed that stars which are more than about a solar mass, that is roughly as heavy as our sun, would unstoppably collapse. So the exact statement he used was that, he didn't actually say what would happen to them, but he said one is left with speculating on other possibilities. Now, a few years later, Oppenheimer and Schneider actually investigated this much further. They investigated the collapse of very, very massive stars, and they found that they collapse to a point where the curvature comes out to be infinite, which is what which was the Schwarzschild consequence. And they correctly interpreted this as a surface and as sort of an information horizon. And they said that a star that collapses like this will close itself off from any communication with a distant observer. And so anyone outside that sphere would only sense the gravitational field and would not receive any information from within. Uh, but there were still many questions about this. And there was skepticism that these things were real. So, were they really real? Was it just an artifact? And would the matter, even if a star collapsed like this, would the matter eventually somehow come out? Could there be some deviation from symmetry which would prevent such a collapse and this infinite curvature which nobody was happy with? Or could quantum physics effects prevent such a collapse? So there were lots of questions. And as a result, what they found were considered to be mathematical artifacts rather than anything real. But the scene changed in the early 60s. So some strange objects were discovered, and they were called quasars at the time. They're still called quasars. And so these were they look like just regular pinpoints of light. So this is one example. This is the first example. So here you see a picture of the sky, and here, over here in the center, is this little pinpoint of light, which is marked within crosshairs. And it looks like any other star, but it actually wasn't, because when they looked at its spectrum, it showed features which were nothing like a star. So stars show features just like our sun. So if you look at the spectrum of a star, you could do that, some of you have probably done it using a CD and seeing the reflected light of the sun off of CD, and you see this sort of a rainbow, and then you see these black lines in between, which represent the atoms in the outer atmosphere of the sun absorbing some of the light. Here, on the other hand, you don't see black lines, you see the opposite, you see emission lines. And even the rainbow-like background, which you would see in a star, is not seen in this. So it was very, very strange. They looked like stars, but when you dug deeper, their properties looked very different. And it was up to someone called Martin Schmidt, an astrophysicist who was studying the properties of these objects, to realize that they looked strange only because we couldn't recognize all these emission lines, as we call them, all these features in the spectrum. And the reason they were not recognized in the very beginning, first off, was because they were shifted from what we are used to in the laboratory on Earth. And those days it was realized that if you saw such features shift by large amounts, that meant that was a measure of how far these objects were. And so it was realized that this strange object, 3C273 was its name, was extremely far away. And if it was still as bright as we saw, then it must be very, very luminous. In fact, it was so luminous that it emitted as much light as all the stars in the Milky Way put together, or Andromeda put together. And in fact, George Gamow came up with this poem, "Twinkle, twinkle, crazy star, biggest puzzle from afar, how unlike the other ones, brighter than a billion suns. Twinkle, twinkle, crazy star, how I wonder what you are." So not only were these very, very luminous, or very, very powerful, they also changed. So it was noticed that the brightness of these pinpoints changed over time scales of weeks or months, or sometimes even days. Now, this is something very, very important, and I'll explain why. Because if something changes so rapidly like that, it means that it is also this changing light is coming from a very small volume. So we call that the light travel time argument. It's a very simple argument, actually, but it is not part of our daily experience because we think of light as traveling instantaneously. But the fact is, the light does have a speed. It travels only at 300,000 kilometers a second. So, for example, it takes light more than a second to reach from the Earth to the Moon. So what is this light travel time argument? So just imagine that you have some object, which is represented by this gray circle, very, very far away in the sky. And the time I have represented as increasing from left to right. So as we go along, you go from left to right. Now, suppose you imagine that at some point in time, this gray looking object instantaneously brightens, let's say. And we are watching it from this telescope here on Earth. Now, when it brightens, we don't immediately see that it brightens. Right? For example, if the moon brightened for some reason, we would only see it a second later. And if the sun, for some reason, brightened, we would only see it about 8 minutes later, because light takes time to come from there to here. And now suppose you imagine this hypothetical object, which instantaneously brightens. The photons from the front surface of this thing would reach us first, obviously. And the photons from the back surface would reach us later. And the ones intermediate would reach us in between. Now, if you see that something changes on a time scale of, say, 10 days, then that thing cannot be bigger than the distance light takes to travel those 10 days. You see, because there is already, even if it instantaneously brightens, we will see the brightening, we will not see the brightening instantaneously. We will first see the photons, the brighter photons from the front surface, then from the next surface, and the next one, and the next one. And finally, we will see the photons from the very back of this object, because those photons will reach us last. And so there will be if you sat on this object, you might have seen the instantaneous brightening, but here on Earth, we will not see an instantaneous brightening. We will see a delayed increase, a gradual increase in the brightness. Now, how much time will that take? That will take as much time as it takes light to travel from the back surface to the front surface. So if you turn that argument around and you say that, okay, I saw something brighten over a time scale of 10 days, then you can conclude that that object, whatever it is, we don't know what it is, but whatever it is, cannot be bigger than the distance light travels in 10 days. So this was a very, very powerful argument. And this object called 3C273, the spin point of light, not only was it so powerful that it had as much power as a billion suns put together, as George Gamow said in his poem, which is like the light from all of the Milky Way, or all of Andromeda Galaxy, just from a pinpoint of light, but it also changed on time scales of a few days, which meant that all of that enormous power was coming from a relatively small volume. So variations in light tells us about the size of the light source, and the only way to explain this enormous power was to say that there must be this black hole-like thing in these objects, and when matter approaches that object, they would swirl around and plunge into the object, and in the process, they would produce all this power. So this was said by several scientists, including Salpeter and Zeldovich and Novikov. So in other words, we really needed the kind of objects that Oppenheimer had talked about. And near the horizon, we could harness the gravity, the enormous gravity that would be there, to produce the power that appeared to originate in these objects. So the questions remain though, but now there was a really powerful reason to investigate whether black holes could get a more solid grounding than they had. And it was Roger Penrose who had the answer. He used his enormous geometric intuition and very, very innovative mathematical methods to show that actually, even without a lot of assumptions, Oppenheimer and Schneider were right, and that you could have stars collapse. And when they did that, approaching a point where the curvature was infinite was inevitable. And he also showed that this complete collapse resulted in a spherical surface, just like Oppenheimer had found, which has a formula that Schwarzschild had derived, and it represented a surface of no return, so to speak. So inside this, which was called the horizon, all directions led to the future. There was no turning back. And all directions led to the future until a sort of an end of time, which was at the center of this construct. And although that end of time was not a very comfortable idea, and it was realized that new physics was needed to explain it, at least what was true was that this surface shielded that point, which was the end of time. And so, as long as you were outside the surface, you need not worry about what happens inside the black hole. And so, therefore, this deep discomfort that people had with black holes ended, and black holes got to be put on solid ground. So I've shown here the figure that Roger Penrose drew in his original paper in 1965. He always drew very evocative, simple but very evocative figures to explain his ideas. And so I just reproduced that here. So before proceeding, I have one more digression to make. So I want to explain what false color images are. So this is a picture of a cat, and this is how we would get a photograph of a cat if we took one. Now, suppose we photograph that cat in the infrared. Then this is an example of such a photograph. But what does it mean? Because the human eye can't see infrared, right? So when we take pictures, especially in frequencies which the human eye can't see, there are many ways to render it, but the most popular way is to use the idea of false color pictures. What that means is here in this picture, in this infrared picture of the cat, the colors don't represent real colors, they only represent the intensity. So in other words, in this particular picture, the white color represents very low infrared intensity, the orange represents very high intensity, and the blue, etc., represents something in between. So we know that a cat's nose is cold, so there would be less infrared emission from it. Its eyes and ears are warm, so there would be more. And that's what a false color picture would be. Now, this is also a false color picture of a cat in the infrared, but the colors are different. So that's the whole point, that the colors are not real. So the colors are arbitrary, and whoever does the rendering can choose random colors. So the only way to actually represent this correctly is to give a key alongside the false color picture, which tells you what color represents what intensity. So the colors are arbitrary. This is another representation of the same thing, but this has a key here, and it tells you, which color represents what. So I'll give a couple more examples. So these two galaxies are actually true color pictures. They are pictures obtained by telescopes, but then rendered in a way by mixing the red, the green, and the blue. They're rendered in a way that our eyes would see. On the other hand, here is the planet Uranus, and these are the exact same data, but on the left is a true color picture, where you can see that it's bright over here and then darkening over the edge, whereas here it's a false color picture where colors denote intensity. So orange denotes the brightest and white denotes the faintest, and you have in between colors. So that was a digression about false color pictures, because I'll be showing a few of those. So here was Roger Penrose, who put black holes on very, very solid formal grounds and said collapse of a star into a singularity was inevitable. Meanwhile, the kind of the objects I spoke about earlier, quasars, which had this enormous power and coming from a very small volume, it was determined that they were actually at the centers of galaxies. Not only that, when they were imaged at radio frequencies, it was found that not only was there this enormous power coming from the very center, which was sometimes even brighter than all the stars of the galaxy. So here's an example, and here is a galaxy of stars. This smudge is actually a galaxy of stars. And from it, when imaged in radio, there were these jets of plasma which came out not just from the center, not just from the galaxy, but they went out into outer space. So these enormous jets of plasma, which were hundreds of thousands of light years across. This is another example, again, a false color picture. Here, both the visible light picture and the radio frequency picture are in false color. The blue is visible light. So you see a whole lot of blue smudges, which are mostly galaxies or stars scattered around. But this one particular galaxy in the middle, when imaged in radio, it has this enormous amount of radio emission. Not only that, you can see that the radio emission is not just coming from everywhere, but coming from this very directed, outward flowing stuff. And we know that that is actually plasma. Now, how do we know it is going outward and not coming inward from outer space? Well, the centers of these things have been imaged with very sharply and over time. And this is an animation which has been put together by taking such images over time and putting them, one after another to create an animation. Why doesn't this work? Ah. Okay, for some reason this animation is not playing, but you can actually look this up on the internet, and what it is showing you here, what we see is these represent the blobs of plasma, the same blobs of plasma that we see here, but on a much smaller scale, very close to the center of the galaxy, and we actually see them moving outwards. So we know that these things we call jets are not stuff which is going from outside in, but actually stuff which is coming from inside out. This shows a simulation of how this might occur. So what you see there represents the material that is swirling around the black hole, which is at the center of a galaxy. And there's a lot of plasma, so there's magnetic fields, and the green lines actually represent the magnetic field lines. And because this material is moving around, these field lines, which would have otherwise just been straight, get twisted like this. And as a result, they are able to launch some of the plasma outwards into these jets which go outside the host galaxy. So there is a black hole, and stuff which comes close to the black hole does swirl around it and eventually plunge into it. But some of the stuff, because it's such an energetic process, and because these magnetic fields are created which are able to launch, some of that stuff doesn't plunge into the black hole, but instead gets launched outward as jets of plasma. So there were these hundreds of quasars which showed that they were in the centers of galaxies. They showed this enormous power from a very small volume, and they also squirted out these bipolar jets of plasma out into intergalactic space. And the only way to explain it was by saying that there was a giant black hole in their centers, and then harnessing the gravitational force near the black hole could produce all these things. But that was still only circumstantial evidence. So basically, this was the argument that was being used, that when you have eliminated the impossible, then whatever remains, namely the black hole, however improbable, must be the truth. So until then, it was just that. But people really wanted direct evidence. And direct evidence means that they would want to measure the mass of the black hole. And the hope was that if there were things swirling around and plunging into the black hole, and we could actually see them. Remember that in these objects, we don't actually see the stuff swirling around and going into the black hole. What I showed you here was only a computer simulation. And what we see here are images, they're static. We are not seeing the dynamic process of stuff which is swirling in and coming out, because we don't have sharp enough imaging to do that. So therefore all this is just circumstantial evidence, it's not direct evidence. But we really want to see direct evidence. That is, we want to see things which are actually moving around the black hole, just like the planets move around us, our sun. And if we see that, then if we measure the speeds and if we measure how far these things are from that putative black hole, then we can derive the mass. So that was the Holy Grail. The best case for that was our own Milky Way, because the Milky Way, as we know, it's a galaxy of billions of stars. And if it was true that these giant black holes sat in the middle of galaxies, then our Milky Way should also have one, because our Milky Way is an ordinary galaxy. It's nothing special, so it should be like any other galaxy, and therefore it should have a giant black hole in the center. Now, this shows you the Milky Way. So here's the Milky Way. This is a beautiful photograph taken by my friend Dorje Angchuk from Leh. And you can see that the Milky Way is made up of many, many stars. We all know that. This is where the center of the Milky Way is. So this is the Sagittarius A constellation, which is like a teapot. And the center of the Milky Way is marked here by this circle, which is close to the spout of that so-called teapot. But what you see is that the Milky Way has a lot of dark patches as well. Why are these dark patches there? Not because there are no stars there, but because in between the stars, there are dust particles. And of course, it's a very, very tenuous atmosphere, but nevertheless, the distances are so vast that there are enough dust particles in there to obscure our view of the stars behind it. So dust particles tend to scatter the light coming from behind, and therefore we don't see what is behind them. So they look dark. So these patches are because there are dust particles in there. So we know, so this is not a real picture of our Milky Way. Obviously, we can't take a picture like this from outside the Milky Way because we've never traveled that far. But we know from the study of the Milky Way and from seeing how stars move and how the gas moves and so on, that the Milky Way is roughly spiral shaped. And the center of this Milky Way is roughly 26,000 light years away from the sun. So this is just an artist's picture to show you that. It's not a real picture. So around the 80s, okay, I forgot to say one thing. So the center of the Milky Way, I said, is in a place where there's a lot of this dark stuff. So we can't actually peer into the center of the Milky Way with visible light because all these dust particles hide the center of the Milky Way. But around the 80s, infrared telescopes started to get built. So infrared detectors started to get built, and infrared light can penetrate dust particles because the frequency, the wavelength of infrared light is larger than these dust particles, and so dust particles are transparent. Not the particles, but these dust clouds are transparent to the infrared light. So with infrared telescopes, it was possible to peer into the Milky Way. And there were these studies. For example, there was a study by John Lacey and Charles Townes it was called The Nature of the Central Parsec of the Galaxy. And they talked about how there is suggestive evidence for a giant black hole there. There was another paper based on studying the stars in the center of the Milky Way by Reinhard Genzel and collaborators, and they said evidence for a massive black hole at the center of the galaxy has been accumulating. But this was still just a couple of steps behind actually saying that there was a giant black hole there. They went up to saying the dark mass is either a compact cluster of 10 to 20 black holes of a few solar masses, or a single massive black hole. That's as far as they would go. Now, what are the challenges? So the one challenge I already said, there's a lot of dust there, so we can't peer at it with visible light, we have to use infrared light. And infrared detector technology was a bit behind visible light technology at the time. The other thing was that our atmosphere distorts light that comes from the sky. So if you have a star, for example, if you look at this animation, if you have a star in the sky, you expect the light rays to travel straight into our telescope, but we have the atmosphere in between, and the atmosphere has a lot of density changes. So what do these density changes do? They start to bend the light rays in all different directions. So the light ray, instead of coming and landing on our detector straight, it dances around, and that is what is shown in this thing here on the right. So the light dances around in this way, and we don't have sharp enough images to catch that. So the only way to catch it in some sense is to have a sensor which can catch those photons before they have shifted around. And this technique, uh, if you don't do that, then the images are not sharp because the light is dancing around and it blurs the actual image, which was what was happening at the time. But uh, by developing this technique of catching the light before it dances around, there were these images that were made by Andrea Ghez and her collaborators. So what is shown here is, so on top is again the center of the Milky Way, and with the blue circle I show the position of the center of the Milky Way, and here I show the image, one of the images that she took. Now this looks like nothing. I mean, you see all these smudges. So what are they? Basically, each of these smudges is created by a star. And it is looking smudged like that because it is dancing around, but this image has actually caught the star, you can see, as it is dancing around. So it is not one big smudge, but several small smudges. So when that happens, they are actually able to reconstruct what could be the original star, and that is what is done here on the right. So you can see that corresponding to each of these smudges, by correcting for that dancing around, they are able to show that there is a star in that position. So this smudge corresponds to this star, that star, that star, and that one. So therefore, they were able to image stars in the heart of the Milky Way. Now, this was huge. This was a huge step. Now, what did Ghez do? She and her collaborators did this measurement at different times. So once in 1995, then in 1996, and then in 1997. And they saw the star positions shift, so which is what is shown here. So for example, this is just one star photographed at different times, 95, 96, 97, and you can see that the star has moved. So if the star has moved, you know in what time it has moved, you can derive its velocity, and you can derive how far it is from the center, the very, very center, Milky Way. And so they concluded that the dynamical evidence leads us to the conclusion that our galaxy harbors a 2 million solar mass black hole, 2.6 million solar mass black hole. Now, at that time, a new development took place, which was the building of the so-called Keck Telescope. Now, this was an enormous telescope. It was cutting edge at that time, and it had a mirror which was 10 meters in diameter, which was among the biggest. So if you have a large mirror, what that means is that you can collect a lot of photons. And therefore, you can take these very quick pictures much more precisely. It was also atop a mountain called Mauna Kea in the island, one of the islands of Hawaii. And so using this telescope, Andrea Ghez could take images which I will skip this thing about the telescope, which were much more precise and gave much more precise speeds of these stars. Reinhard Genzel did the same thing with a new technology telescope in Chile, which was the European telescope. And then there was another technology development, which was that using a laser. So they developed this mirror, which was actually not, it was a 10-meter diameter mirror, but it was not a single mirror. It was a mirror, you can see it here. It was a mirror made up of smaller segments, which were hexagon shaped. So this hexagon is one segment of the mirror. Similarly, there are many, and they're all put together to make one big mirror. The reason to do this is that, I will explain it very quickly, is that you can control each of these segments independently. And so what they did was they had a laser beam. So they point the telescope at some part of the sky. They project a laser beam, which goes through the atmosphere and, in a sense, measures the density gradients in the atmosphere. Then they predict what would be the distortions that would result in. And then they control the segments of the mirror to compensate or correct for those distortions. So that what you get eventually is a corrected, much sharper image, which is not affected by the blurring of the atmosphere. So that was what was done with this telescope. This is called the technique of adaptive optics. And you can see here an image of Uranus on the left without the technique. So you can see how blurred it is. And on the right, with this technique turned on, that is, with a laser beam measuring these distortions of the atmosphere and then controlling this. The orientations of the segments of the mirror in real time to correct for those distortions so that you get a much sharper image. And this is showing you, for example, the impact of that. So this is the center of the Milky Way. These are those same 4 stars that I showed you earlier, 1, 2, 3, 4. And you can see that this is without that technique of adaptive optics or correcting the atmospheric distortions in real time. And this is with corrections. So you can see very clearly that, first of all, those stars are very clear. And second of all, you can see many more stars because now there is not that much blurring. So even some of the fainter stars, which are close to these other stars and so on, they all become visible. And so by repeating such images over time, Andrea Ghez was able to determine the velocity and therefore the mass of the giant black hole in the center. So what I'm going to show you now are her data, and I want to explain that. So what is shown in the center, this is a false color picture of the center of the Milky Way, and each of these multicolor splotches represents a star. Now the stars have been labeled SO2, SO54, etc., etc. And on the top right is a counter which gives you the date when that image was taken. So there was a sequence of these images taken right from 1995 all the way down to 2019. And then you put those images one after another. And so you see how these multicolored splotches shift. And that's real data. The multicolored dots here, they are real data, they are real stars. The white star-like thing in the center is not a real star, that is just marking a position, and you will see why. So let me show you the animation now. So you can see that these splotches are moving. And you can see that these stars are, they're first of all not moving in straight lines. You can also see that they're not moving randomly. They are moving in these almost elliptical-like orbits around the same point, which is marked by that white star. So it's sort of like the way the planets in our solar system make elliptical orbits around the sun. So all these stars are moving around that point marked by the white star-like thing in the middle. And what is more, if you look at the very closest star, that thing which just passed that white point, it has gone very close to it, but has emerged from it unscathed. So obviously there has been no collision. So whatever it is, this dark thing with enormous mass that is driving all these stars in elliptical orbits, it has to be smaller than that distance of closest approach of this star. right? Otherwise, we would see the effect of a collision and the star would just deviate from its path. So that gave a limit on the size of this thing, and the mass was derived from the Keplerian formula by, as I described before. And so their conclusion was that the black hole at the center of the Milky Way is 4 million times as heavy as our sun. So that was direct evidence, dynamical evidence for the existence of a giant black hole. Now, this was in the late 90s, and subsequent to that, in 2015, all of you know of this result where gravitational waves were found from two black holes that coalesced, which created ripples in the space-time fabric. I don't want to go into details of this, but this was another uh, direct piece of evidence for black holes being real. So one did not have to invoke the Sherlock Holmes argument because this was direct evidence. It won the Nobel Prize. And I would recommend the talk that Gabriela Gonzalez gave at the announcement of this discovery, which is a very short talk, but it's a very evocative talk and describes beautifully the result. But how do we really photograph a black hole? Because this was still not an image of the black hole, it was not a photograph of the black hole, right? Now, naively, you can't because the black hole is black. But if you have stuff that is going around it and shining, maybe you can image the silhouette of a black hole. So how would you know it's a black hole and not just some regular object? In the case of the black hole at the center of the Milky Way, we know it is a black hole because it is an enormous amount of mass in a very small volume. And it fits with that formula which John Mitchell and Laplace and later Schwarzschild derived, right? But if you imaged something you think is the silhouette of a black hole, how do you really know that it's a black hole? So here I show, this is not a real image, this is an artist's impression. What would happen to an ordinary spherical dark object? So suppose you have an ordinary massive dark object, which is not a black hole. And you had, let's say, stuff coming near it. Now the stuff would be attracted by its mass and start swirling around it and maybe eventually fuse with it. But in the process of swirling around, this stuff could get accelerated if the gravitational field is strong enough, and then it would shine, and we can measure that shine. But the black hole, the dark object itself, I said, is dark, right? So you would have this dark object, and you would see its silhouette against this shining stuff which is swirling around it. So it would look something like this. But what if that's a black hole? We know that Einstein's theory of gravity predicted that light bends in the vicinity of massive objects. Now, the black hole is among the massivest objects we know. And so the light from very close to the black hole would bend as per Einstein's theory. And so what we would get is this. So I'm sure many of you have seen the film Interstellar, where there was a fictitious black hole called Gargantua. Now, the picture of Gargantua that was shown in Interstellar was a result of a proper computer simulation using correct physics. So this is what they predict it would look like. Why would it look like this? So you have this black hole, you have stuff swirling around it and eventually plunging into it. And because the stuff is swirling around, it's accelerated to very high speeds and therefore heated, and therefore it shines. All this stuff would shine. Now, if it's an ordinary object, then, and you are looking at it from here, let's say, from the front, then you would see all this, which would be shining. But you wouldn't see this because that would be behind this dark object and it would be hidden by it. But if it's a black hole, the light from that would curve around the black hole and still reach you. Similarly, the light would curve around the black hole from the bottom and still reach you. And so you would see this light from the shining stuff from here, the shining stuff from here, and from the front. In addition, you would see the light from the shining stuff from the back bending. And that is why you would get this top hat kind of picture, which was what was Gargantua. And that is what you expect of the silhouette if it is a black hole. And this was what was done by something called the Event Horizon Telescope, which is actually an array of telescopes. It's not a single telescope. So this telescope uses the principle of interferometry. And so each telescope in this array is effectively an element of that interferometer. So you have these pairs of telescopes, each of which becomes an interferometer. And so this shows you the map of where these telescopes were located, some of them in South America, one even at the South Pole, and others in North America, in Europe, and so on. And so this interferometric array is built in order to get very, very sharp images of the sky. So with single telescopes, there is a limit to how sharp an image you can get. But at radio frequencies, the technology is advanced enough that we can build these interferometers and look at the sky and get the sharpest images ever. Of course, they need a lot of offline processing. So, for example, I talked about how Andrea Ghez used this segmented mirror, and in real time, they would correct the distortions of the atmosphere by compensating for them by distorting the mirror. Uh, this does effectively the same thing, but it does it offline, not in real time. And by doing that, they are able to get the sharpest images ever of the sky, though at millimeter wavelengths. And this is Katie Bauman, who headed that software effort. So she's not an astrophysicist, but a computer engineer, and she was one of the people leading the effort to create algorithms to create these images from the interferometric data. And they looked at this galaxy called Messier 87. And so this is the visible light picture of the region of the sky containing Messier 87. So in the center is Messier 87, which is a galaxy of billions of stars. These cross-shaped things are foreground stars in our own Milky Way. And all these smudges that you see are galaxies in the background or the foreground. But they focused on this. And this is a zoom in. And Messier 87, when imaged in radio frequencies, shows these bipolar jets of plasma which come out of the center and go out into intergalactic space. And the size of these plasma, they become actually lobes, and the size of, because the plasma diffuses out into intergalactic space. And so the size is enormous. And what the Event Horizon Telescope was looking at was the very, very core here, the very center, which you can barely see on this image. And this is what they found. In other words, they found what one would predict from general theory of relativity, namely the silhouette of a black hole. So that is the most direct evidence, you can say, for black holes. So I will stop there and I'll take your questions.
Thank you, Prajwal, for taking us through those three avenues, exciting avenues from where we found no need for Sherlock Holmes. Three very exciting ways of direct detections. And uh, actually, all of you participants, in case you have not been here for the earlier lectures, if you just type your question on this, I can, Prajwal, if you
Yeah,
are on your full screen tab, you would not be able to see the questions that I flash in the studio. Would you be able to come to the studio tab? Of course, I'll read out the questions too. And this was
how
business.
do I can
Uh,
see the comments in the Steam.
yeah. Even that, yes. Viswanath Jana, while you had just started talking about space and time and so on. At that time, he had asked, but I didn't want to disturb you, so I didn't put forward that question that time. Is space time fabric distributed everywhere in the universe, or it's an imaginary concept?
Well, I'm not sure I'm the right person to answer whether it's real or not. All I can say is that the space time idea is a different way of thinking about gravity, which Einstein talked about. And all the experimental evidence so far supports that idea. So, all the predictions, so I mean, if you ask me, have you touched space time, or have you seen space time? Obviously that's not how one thinks about it. That's apparently not the right question to ask, I would say, about space time. But whatever has been predicted by that theory, by the idea of space time and how masses curve space time and so on, all of them have supported, are consistent with the predictions. So all empirical evidence so far are consistent with the predictions, including, so what I didn't cover today is the very, very current state of the art of this Milky Way Center experiment. So both Andrea Ghez' group and Reinhard Genzel's group have made even more advances and have sharper images now. And so they've been tracking. So that one star that I showed, which came very close to the center of the Milky Way, that one star they've been tracking for more than an orbit. And so they're able to now test predictions of the general theory of relativity on the orbit of that star and so on. And so every bit of evidence so far is consistent with the predictions of the theory. That's as
Eh,
far as I.
Yeah, that has also probably answered your question, Swift, who wanted to know about space time. And everyone, and myself included, have enjoyed the talk enormously. And yeah, so Amresh Verma is saying that he was always confused about the black hole picture, but not anymore after
Oh,
today's
thank
talk.
you.
And everyone, has been appreciating the talk. Let me just look up the questions.
So the
Mm,
black hole does not
this is
escape the light, so that if we have to escape from the black hole, then our speed should be greater. Yeah, exactly. As far as once you approach the black hole, you cannot escape from it. That is clear. But before you actually plunge into the black hole, other things will happen, which you have probably heard about, like spaghettification, for example, and that is not because of the black hole per se. I mean, in the sense, that's not because escape velocity is the velocity of light per se, but because the gravitational field is so strong that the gravitational field felt by an object would differ between one end of the object and the other, and therefore it would tend to tear apart the object. So if you have a relatively small black hole, like a stellar mass black hole, then it would be very hard for things to approach it without getting destroyed first. On the other hand, if you have a giant black hole, like in the center of the Milky Way, like Gargantua. If you remember, in Gargantua, the protagonist actually approached the black hole. The reason is that when you have such a giant black hole, the sort of disruptive tidal forces near the black hole are not that strong. And so then the kind of things that were shown in Gargantua are actually possible. But once something crosses this so-called event horizon, crosses this surface, uh, as Penrose showed, all directions lead to the future, and there's no turning back. So one cannot come out of there. Um,
so that's
there's a question: if we accept that gravity is due to the curvature of space-time, shouldn't it also cause repulsion as it causes gravity? Sorry, I don't understand that. I don't understand that question. Ratna, do you have some insight? Why should there be repulsion? Why is this person saying repulsion?
perhaps
Maybe
it
Should, is
If
there, can they
if the
unmute and ask or something?
yeah, Swift, maybe if you could clarify further, why do you think that there should be? Maybe is it something like curvature, negative curvature kind of a thing? But that is not what is postulated. Swift, would you like to say something more about your question? Why do you think it should cause a repulsion? If you postulate that there is maybe some negative curvature or something, what is it that? Okay, Sunita, why aren't we teaching this to the kid that the force of gravity is actually space-time curvature? Well, maybe not quite to school kids. Maybe I don't think it is there in the school syllabus, or is it? Maybe class 11, 12th or something, perhaps it is included. But more like informal education ventures of this kind are perhaps more suitable for, instead of involving children with more complex aspects as part of the syllabus directly. I think maybe more informal spaces are better. What do you say, Prajwal?
I'm wondering actually, I think it's a very good question this person has asked. Uh, I'm wondering that is it a failing of physicists that we think it's very difficult and therefore cannot be taught to small children, and maybe it's not that hard. I mean, maybe not small children, but high school. Maybe it's not that
Hmm.
hard a concept because, after all, Einstein came up with the idea by doing this thought experiment, and that thought experiment itself is a very obvious kind of experiment. You know, so maybe it is our failing that we haven't found a way. We haven't found the pedagogy to teach this, and maybe we should. I think that's an excellent question. Gives a lot of food for thought.
Yeah. Uh,
So, do
Swift.
questions come on the YouTube as well, or what?
Yeah. There are two YouTube links, so there may be people watching from either of those. And if they ask they type a question, it comes into the studio. So if you
Oh, I
said,
see,
"Can I
I see.
ask?" Go ahead, please go ahead and ask whatever you wish to ask. So you just have to type it. If you want to ask directly as audio video, then you'll have to come into the studio. That takes up unnecessary time. It may be faster if you just type your question on YouTube. Let me just see if I have missed any question from earlier. Um, uh, I'm just checking. Mostly everyone has been appreciating the talk, and yeah, you really did build it up step by step. Why we should invoke Sherlock Holmes, and then why we should ask him to leave. So if you said you want to ask something, so please go ahead, type out your question. Maybe type it in bits and pieces if you like. Uh, all right. Yeah. Anybody else, if they would like to ask any question, please go ahead. So that the animation that is showing this, so one of them had almost like a straight line kind of a path, right? Very narrow ellipse. That is the one
Right.
you said, that almost it looked like it has come
No,
and
no, that
collided.
is no, not that one. The one which is marked SO2. I'll just go to it. My
Let
screen still visible.
Yeah, I put it back. Yes, it is there.
Okay, how do I get to my?
Maybe back, just yeah.
So, so this thing with the yellow colored orbit, that one, which went very close. Um,
Yeah.
so it's called SO2. See, you can see it here. It's this one, SO2,
Mm-hmm.
and that's the one. It has an orbital period of about 16 years. So now, since 1995, now it's completed an orbit, and it's come back to the place where it started from. So they will actually be able to measure its precession if there is any, and so on. And so test further the predictions of general relativity. So this is 2020, as you can see. It could well be that they keep. So you should Google this thing, Keck UCLA Galactic Center Group. They have wonderful material which has come from their results. Absolutely great visualizations and renderings. So it could well be that this plot of mine is out of date and they have more
Hmm.
data.
The millimeter wave observations, they have not yet. I mean, there are still some issues with respect to the galactic center. And are there any other candidates one might expect over a period of time to have more such?
Yeah, the millimeter thing. So with the Milky Way, the problem is that in unlike the Messier 87 case, so the Messier 87 case, it has these jets of plasma. It has the accreting black holes, so stuff swirling around it, which creates this, because it's shining. It creates this very high contrast between. Um, between the stuff around and the central black hole. The problem with the Milky Way black hole is that it's a relatively benign or dormant black hole. There's not a whole lot of stuff in its vicinity which is swirling around it and plunging into it. So there isn't that high contrast between the stuff around and what's plunged. And moreover, because it is so close by, within a period of observation, there will be changes. And so then that makes the whole data analysis process much more complicated. So they're still working on it, and we hope that something will happen. The thing with Messier 87 is it was in that sweet spot, because so we need sharp images, which means that the silhouette of the black hole has to be big enough that our images can actually see it. Now, the more massive the black hole, the bigger its silhouette will be. The further the black hole, the smaller it will be, as seen by us, because the size, the angular size actually gets smaller. It's like an aeroplane will look smaller and smaller as it flies further and further away. So Messier 87 has a billion solar mass black hole, and it is yet close enough that we are able to see it. So other black holes are either not large enough or too far away. So Messier 87 was in that great little sweet spot. There are not that many, lucky for us, objects. They've imaged a lot of objects where they've seen the launching of these plasma jets from very close up and all of that. But the silhouette of a black hole, that it's only for Messier 87 that they've been able to see.
So there is this, and there was one other question. As AC textbook say that speed of light is constant. It is true. Is it so? It is. It's as a postulate of Einstein's special theory of relativity. It is constant, and we haven't come across anything to counter
Yeah,
that
right.
question. And there is one student who is asking question. It's not very clear what he's asking. He has asked for the link to the studio, so maybe he'll come in. But meanwhile, Aditi's question.
I would
Uh,
like to ask about gravitational constant. This depends on the mass of an object. If I could go to Jupiter, then G will be changed for me. So why is this called universe? No, that's not true. So it is indeed a constant. I mean, of course, it's
yes.
yeah. People have investigated whether it changes with cosmic epoch and so on, but as far as we know, it's a constant. So it would not change on Jupiter or on the moon or
And,
anything.
there is this question: how much black hole in must be asking how many?
Huh?
Or
How
how
many
much
black
of
holes
the
in the universe? Yeah.
mass? Or maybe how much of the mass, total mass, is in black holes?
Yeah, that I wouldn't be able to answer how much of the total mass, but just to give you an idea. So one point that I kind of glossed over in my talk was that when a star collapses, I talked about stars collapsing into black holes, right, in the very beginning. But then later on, I didn't talk about what is the empirical evidence for such stars which have collapsed into black holes. I skipped that whole. That's a whole story in itself, and it is sort of ironic that the evidence for the giant black holes we got much earlier than the evidence that these collapsed stars had found black holes. So, but they are there, and so stars which are beyond a certain mass, they when they die, that is when they finish all their fuel and they die, they expel some of the mass. But if the remaining mass is more than a few solar masses, then they are expected to collapse into black holes. But it's hard to find them because they will be black. But the way they are found is sometimes you have such stars which are in a binary system. So they are gravitationally bound to another star. Now, this star may collapse into a black hole, but that star will be happily shining away. And when that happens, some of that the effect of this black hole will be seen on the orbit of that star, for one thing. So you will see that star wobbling, even if you don't see its companion, because the companion is a black hole. You will see the star wobbling, and sometimes this other star, the shining star, in the process of its growth during its life, it would expand. It could expand, and if it does that, then some of that material would get sucked into this companion black hole, and as a result, this black hole would become an X-ray source. It would emit very, very brightly in X-rays. So that would be a very nice way to find them. And such objects have been found, their X-rays measured, and then the companions wobble measured, and from all that you can actually determine the mass of this black hole. And there are several known. There is a catalog called Black Cat. So if you Google Black Cat black hole catalog, you will get this catalog where these people keep updating the black holes as they're discovered. And the last I checked, there were about 66 known. And these are all within our Milky Way. And using astrophysical methods, one can predict how many there are. I mean, we can only see the ones, first of all, they have to be in binary systems, they have to be sucking up this stuff from their companion and be bright in X-rays and so on. So only then we can discover them. But there are ways to estimate how many there could be. And the estimates are that there must be about 10 million stellar mass black holes scattered all over the Milky Way. And therefore, every galaxy would have roughly that many stellar black holes scattered all over the Milky Way. Every galaxy would have a giant black hole in its center. And this image that Ratna is showing as the background, it is the Hubble field. It is an image of a very, very small piece of sky. And that small piece of sky shows 10,000 galaxies in it. I mean, every dot and smudge on that image in the background, which Ratnashri has put, is a galaxy, and it has a giant black hole in it. And so, and there are 10,000 galaxies in this small area of sky, which is about the 10th of the size of the moon. So you can imagine in the whole universe, how many galaxies there are, and therefore how many giant black holes there are, and even how many stellar mass black holes there are.
There was a
Okay,
student
so
whose
somebody
questions were
has come on.
uh,
Yeah, yeah.
not very clear, so he has come into the studio. Please quickly ask Shreyash. I could not make out the full question there. Yeah, could you
Yes,
please
ma'am.
go ahead and quickly ask?
Ma'am, what is space-time, and if we accept that gravity is due to the curvature of space-time, shouldn't it also cause repulsion as it causes gravity?
Uh,
Yeah, I don't
you
I
you
don't
already covered
understand
that
why you think
question,
there should be
right?
repulsion. Yeah, why do you think there should be repulsion? Because what gravitational theory is saying is that there is this sort of, imagine a fabric. I mean, imagine a piece of cloth and you put something really heavy in it, and that cloth will bend. That's an intuitive way of understanding how mass curves space-time. Of course, actual space-time is three-dimensional, and this cloth is only two-dimensional. So you have to extrapolate, and it's very hard for the human brain to extrapolate, but that at least gives you a pathway to imagine that. But why would you think there would be repulsion? I don't understand that.
Okay, ma'am.
All right. So yeah, stay on for that. Now there are a couple of other just follow-ups kind of thing. I think more of discussion. So
Yeah,
perhaps I
I
mean
think
if
Aditi
time,
Puri is still asking about the gravitational
yes, yes,
constant,
it's
and
about the
yes,
gravitational constant. Yes.
yeah, indeed, there are. I mean, it's a real
Mm.
question which people are investigating. I'm not one of them, but there are people who are investigating that. Yes, so we don't take anything for granted.
Sunita Nair is asking whether every galaxy has a black hole at the center.
So every galaxy, a reasonably sized galaxy that we've looked at, seems to have one. So it is the widespread understanding now that every reasonably sized galaxy does have a giant black hole in its center. Yes, and it'll also have these, stellar mass black holes, millions of them scattered all over the galaxy.
Yes. So, if there are no further questions, we would perhaps be ending the broadcast. Is there anywhere maybe some kind of data experience students could have of any of
Oh
these
yeah, I
missions?
forgot about that completely. I meant to.
We could also
Hmm.
have a follow-up session. We could have a follow-up session if you would be okay with it.
Yeah, but what I encourage people to do is, so there is this formula, right? So first of all, you can derive the formula yourself from your high school physics. That first of all, the formula for escape velocity, which I showed right at the beginning, and is it, yeah, it's visible, right? Yeah. So this formula, and then you set the velocity of light equal to c, and then you get the other formula, which is the relationship between the size and the mass of an object in order for it to be a black hole, which is this formula. So this is a relationship between the size, the radius of the object, and its mass if it has to be a black hole. So what I encourage you to do is to think about the density of such an object. So, people have this imagining that a black hole is very, very dense. And it is true that, for example, if you try to make a black hole out of the Earth, you would have to squeeze all the mass of the Earth into a small marble-sized sphere, and then only it would become a black hole, and that would be enormously dense. It's unimaginably dense or unphysically dense almost. So what I would encourage you to do is, so this is the size, right? So from the size, you can determine the volume, assuming it's a sphere. And so if you have the volume and if you have the mass, you can derive a density by dividing the mass by the volume. So I encourage you to derive that density for different masses of black holes. So what would it be for the Earth? What would it be for the sun? If the sun were to become a black hole, the sun would have to be squeezed to about 6 kilometers diameter. All of the mass of the sun would have to be squeezed to about 6 kilometers diameter to make it a black hole. So what would be the density then, if that is the case? And then what would be the density if it is, for example, the LIGO black hole? So the gravitational wave discovery of the very first discovery of two black holes coalescing. One was about 65 solar masses, and the other one was about 30 solar masses. No, something like that. I think the total was 65 solar masses. So if you have that big a black hole, then what would be its density? And then what would be the density of the giant black hole in the center of the Milky Way? So I encourage you to determine that. And then think about this question: is it really true that black holes are really really dense objects? So that is one exercise I would suggest.
There's one perhaps last question. Aditi again. Black hole does have an accretion disk, so what type of particle emits on this? Hmm.
Right. So I think she means what is the material of the accretion disk, right? So yeah, so the material, it's basically plasma. So it's ionized plasma, but it could have, uh, it is made up of stuff which is around. So whatever, for example, stars or gas that is around in the galaxy is what then, if that stuff comes close to the black hole, it would swirl around and it would become this accretion disk. So it would have the same composition as those things. So whatever stars are there in the vicinity, whatever is their composition, that would be the composition of the accretion disk, except that the atoms would be ionized and it would be plasma.
So, Santosh Kumar Gowda, Stephen Hawking discuss about black hole in the book. So go ahead though, read the books, and you'll find lots of material on black holes, and also a lot of information online if you want to do learning. But you may have to be a little careful to go to sites which give you the real science. Sometimes even some fantasies and stuff. I mean, like the interstellar movies, etc., are fine too. But go to university sites, etc., etc., where you will find content to learn. So I think we will end the broadcast here. And it will be lovely, Prajwal, to have maybe one more follow up session sometime whenever you are free. Thank you so
Sure, we
much
can
for.
talk about stellar mass black holes, maybe.
Yeah, that would be lovely, simply lovely. And so I'm ending the broadcast, everyone. And so
Thank you very
nice,
much. Thanks for listening
nice
in.
questions. And all right, okay.